in our case. When Theia hit the Earth, it created a lot of heat. Theia was destroyed for the most part, and the Earth was partially destroyed. And Theia, which had an iron mantle, lost its iron mantle to the Earth. The iron part of it went into the center of the Earth, so now we've got an Earth with a great big huge iron center, which is good for reasons I'll explain in a sec. So we got the Earth with a great big huge iron center, and a lot of the volatiles, those are elements up at the top of the periodic table. Want to show them the periodic table for a sec, number 40. The elements up at the top of the periodic table, the light elements are the ones that boil off easy, and the ones down here, the heavier elements, don't. So we've got a hot moon right next to a hot Earth. The Earth is thousands of degrees, and the moon, instead of being 384,400 kilometers away like it is now, was only about 25,000 kilometers away. So the moon was picking up all this heat from the Earth. Because the Earth is big and the moon is small, the Earth captured the moon in its gravity and tidally locked it, probably almost right away. So now you've got the Earth turning slowly and the moon turning faster, but they're both turning at such a ratio that the same side of the moon is always facing the Earth. So the moon is turning. It never has not turned, and it will continue turning even as it gradually moves away from the Earth, which it is doing at the rate of 3.78 centimeters a year. So eventually the moon will be a much longer way away, but right now we don't have to worry about it. And the fact that we've got a moon there is a really important thing, because having a moon there stabilizes the Earth. It stops it from tilting all over the place. The interplay of gravity between the moon and the Earth keeps the Earth stable. So that, you remember last time we were talking about Milankovitch cycles?
Yes.
Give me something here, folks. Tell me you remember something about Milankovitch cycles. Well, if you don't, you're asking for it, because I'll tell you all over again. So come on. If you were a class, I'd test you. You guys wouldn't be getting away for this for 1 second. Really, all I want is to feel you're going away having learned something. You just take as much as you want. Anyway, what happened was this guy called Milutin Milankovitch, a Serbian mathematician, was looking to find out a reason why we had ice ages. And he concocted a theory whereby ice ages are caused by three things: the Earth's orbit, the Earth's wobble, and the Earth's tilt. In terms of its orbit, the Earth goes around in an almost circle, but not quite. And if the circle is perfectly circular, it has a different influence on how much radiation from the sun the Earth can pick up. So that's one of the three factors, the orbit. Is it circular or is it a little bit egg-shaped? Egg-shaped means elliptical is egg-shaped, okay? So here we got Milutin Milankovitch. Here we've got the Earth. And what we're looking at here in the middle is something called, it's called the precession of the equinox. This thing we've got here is not entirely accurate. And I'm telling you, you've got to really be careful with AI if you're trying to use it. Because I was trying to find out what exactly the influence of the Earth's wobble was. You see, Milankovitch said, okay, you've got an orbit that is either circular or almost circular. You've got a wobble too, because what happens, the Earth is like a spinning top. When you spin a top, you can see that it wobbles, right? Well, that's what happens to the Earth. The Earth has been spinning ever since it got created, and especially ever since it got hit by the moon. That started them both really spinning, and that probably put the Earth on the angle that it is now. The angle varies from 22.1 to
24.5.
huh?
24.5.
Yeah, 24.5. That's really good. Man, you're smart. And that wobble has an effect on when the seasons occur. But the biggest of the three, out of orbit, wobble, and tilt, is the tilt. The tilt varies from what, 22.1 to 24.5, right? And the tilt is actually called the precession of the equinox, not axial precession. But I'm telling you, you've got to watch it when you look stuff up. The irony is, it's like in the old days when we used a dictionary. You're looking up a word you don't know how to spell. Okay, that didn't go over too well. But anyway, carrying on. Milankovitch then said these three things are why ice ages occur. And he said the biggest reason why ice ages occur is because of the tilt. What the tilt does is determine how much radiation, solar radiation, you get from the sun in the summer or the winter. And the important thing is, if the summers, what brings on an ice age is not cold winters, it's cool summers. Summers where the ice doesn't melt. The snow that falls doesn't melt. So one year the snow falls and doesn't melt. The next year it falls and doesn't, not all of it, right? Over a few millennia, a few thousand years, you've got it converted to ice. Each layer compresses the area, the layer beneath it, and you've got ice. And eventually, what happens is something called the tipping point. I was going to deal with it down here, and I'll deal with it again. I'm not proud. A tipping point is that at that point after which things are irreversible. And what happens in an ice age is, now, we need that one of those ones with the earth half ice, ice at the top, ice all over the earth. Chelsea, okay, hon, I don't know. I just want a picture of the earth covered with ice. Oh, thank you. All right, so here's how it starts. The ice starts at the poles. If it continues to build up because the summers are cool and it's not melting, it starts to move down and up, right? Because this is the warm part and this is the cool part. And when it gets to a certain point, and that point is 35 degrees north or south, when it gets to a certain point, you can't stop it. Because what's happening is that ice has what is called an albedo. Everything has an albedo. That's the amount of light that it can reflect. So if you're standing on an asphalt road, that's not very bright, right? Okay. You know the moon's not there? That's got exactly the albedo of asphalt, and yet it still manages to shine that brightly, which I think is really quite something. So let's hear it for the sun. Anyway, once it gets down past 35, you can't stop it, because at that point it's reflecting so much light that it just keeps getting colder and colder. You got it? Now, what's happening or what happens is, see those oceans? Those are dark. Those soak up energy. And matter of fact, let me show you where things get soaked up. Let's have number 20. I think that's James Clerk Maxwell and the electromagnetic spectrum. Okay. There's your electromagnetic spectrum. This part you can hear. This part you can cook with. This part you can't see, but man, is it important. This part we can't see either, but bugs can. And if you look at your average flower out there, try to imagine as you're looking at it that flower very likely has patterns on it, which function as landing instructions for insects, because the flowers want to be pollinated, right? So they do a couple of things to get themselves pollinated. One thing they'll do is put a nice pattern there. You know, some flowers have got a dark middle. You know why that dark middle is? It soaks up heat because it's dark. It soaks up 6 times as much heat as the light part of the petals, and a flower that's got a dark middle like that can get 6 times as many bugs on it as a flower that doesn't. So sometimes we can't even see that because the patterns are in the ultraviolet. Anyway, this part up here is the part that'll kill you if you're not careful. Gamma rays will destroy your tissue. They ionize your tissue. They lock the electrons off of atoms and cause them to disintegrate, and that creates radicals, and it's just a mess. X-rays, gamma rays, ultraviolet. So a lot of birds and bugs see in the ultraviolet. Now, the infrared. All right, there is this word called carbon. A lot of people don't like it because they think it's a political word, but it is not. And so I'm just telling you straight out that I organized these lectures to be about science. And science is what it's going to be about. And the science is the science says that what carbon does, carbon dioxide specifically, is it soaks up heat in the infrared. Okay, what happens is electromagnetic radiation comes from the sun. So it comes down and it hits the earth. Some of it gets reflected. If you've got a lot of ice, you're going to get a lot of it reflected. If you don't have much ice, it'll get absorbed, right? So dark surfaces soak up light. what I'm seeing here is this coffee cup, which is greedily soaked up every single photon within sight, and I'm seeing black. If it was giving all the photons off, I'd see white. And that's how color works. When you're looking at color, that didn't
You want
work
it
so
back?
well. You're looking at wavelengths. Here I went to dramatically illustrate the Maxwell equation, or the electromagnetic spectrum. So, carbon dioxide then traps, you've got this incoming radiation, comes into the atmosphere, and about half of it gets deflected back out, depending on, as I say, what the albedo is, right? What was that?
Do you want the albedo again?
No, I didn't want albedo. Oh, but the infrared. So the light's coming down, it's getting deflected back out, but some of it doesn't get back out, which is where CO2 comes in. CO2 traps it in the infrared part of the spectrum. And that trapping in the infrared part of the spectrum is what causes the planet to get hotter or colder. So we'll be looking at life on Earth, and life on Earth is inextricably tied up with the surrounding environment. That's what Charles Darwin's Origin of Species is all about. Darwin didn't invent evolution. Evolution's as old as the hills. The ancient Greeks thought about it. Anybody looks at anything and you can see things change. You have to mental giant to see that, right? The point is, how do they change? How do things change and yet stay the same? Life changes, and yet life is always similar to the life that's gone on before. And no two things on Earth that are alive today are identical to the kinds of things that were alive on Earth 252 million years ago, when we had the worst extinction of all time. 96% of everything, all life on Earth, became extinct. Why was that? Because there was too much carbon dioxide in the atmosphere. There was an area over in what is now Russia called the Siberian Traps, and that whole area erupted. That is a big area. It is about as big as Canada. So we had an area erupting 255 million years ago on a scale that none of us can even imagine. And what happens is, when you've got volcanic eruptions like that, you have the completion of what is called the carbon cycle. And so I'm just gonna reinforce something with plate tectonics. We've done Milankovitch, I think we're through. But just remember this, the Milankovitch cycles say that you'll get an ice age under certain conditions, but those certain conditions always include the level of CO2 in the atmosphere. Let me tell you something else about carbon. The word organic, everybody knows the word organic, right? It's a beautiful word. It always, no matter what it means to you, it's nice. You know, it's organic. It's got to be good, right?
It's healthy, eh?
Okay, but organic is such a widely used phrase that basically means nothing, right? So here's what it's going to mean to us from now on. Organic means carbon. So if you go to university and you want to be a biologist like I did, you're going to have to take organic chemistry. I didn't. Organic chemistry is viewed with loathing and horror by all students who have to become biologists. It's just this awful thing they've got to go through. Because organic chemistry is all about carbon. It's all about how carbon bonds with carbon, and about a million other things. So organic in chemistry means of or relating to carbon, because carbon is the molecule which, more than anything else, all life depends on. If you had to choose one atom out of the entire periodic table, number 40.
Oops, sorry. Sorry.
That's Charlie Chaplin and Einstein.
I'm really.
I gotta tell you a story because you weren't here, I don't think. You know, Einstein, right? I mean, everybody knows Einstein. Charlie Chaplin was one of the most famous entertainers in the world. He was a mime. He did his entertainment without speaking. Remember The Little Tramp? Have you ever seen any Charlie Chaplin's? Anyway, I really liked him myself, and so did Albert Einstein. He was Albert Einstein's famous star. Anyway, they finally met, and Einstein says to Chaplin, he says, "I really admire your work." He said, "Somehow you managed to create a universal language where even if you don't say anything, everybody knows exactly what you mean." And Chaplin said, "Thank you, but yours is the greater glory." He said, "Nobody understands what you mean, but they love you anyway." So that's the periodic table. I had it up there for some reason.
You're talking about carbon.
Carbon.
Organic
yeah.
chemistry.
So Thank you, dear. Organic chemistry is about carbon and everything that it bonds with. So you hear people say things like, well, you know, if life came from somewhere else, we'd know it because probably be made out of different stuff. And so would the spaceship and everything else, right? They come from a different part of the universe, different. But no, as a matter of fact, everything in the universe that can be is on the periodic table, at least according to the chemists whose lectures I've listened to. They keep insisting on that again and again. And the best lecture I ever listened to was on the periodic table. I mean, can you imagine anything more boring, right? So I'm sitting there, it's a university lecture, right? So I'm gonna sit there for about an hour. I listened to a lot of these things the last few years. This guy comes out, he's the most boring looking guy in the world, right? His hair's a bit rumpled, his tie isn't tied quite right. Got a suit on, it's not good, not bad, you know. You know, can you imagine, a bit of a paunch, not much, kind of rumply looking guy comes out and he proceeds to talk about the periodic table and the invention of everything in the universe and how the elements came to be, and he shows you pictures of supernovas happening. It is the best friggin' lecture. If you get a chance to view it, the guy's name is Ed Murphy, and it's the periodic table. And it's the most boring thing you could think of, but when you watch it, you realize here is a master. This is the guy I want to be, totally in control of his material, knowing it so well that he can present it in such a clear, vivid, entertaining way that you learn as you go and you just love it. So, The Periodic Table by Ed Murphy, ladies and gentlemen, not the world's most boring lecture. At any rate, carbon is what it's all about. Why carbon? Because carbon can bond with a whole bunch of other things, so it's really good at creating chemical bonds, but the bonds are not too stable. They're stable, but not too stable. See, if you're gonna have an element that you're gonna build life around, it's gotta be stable, and yet it's gotta also be flexible and reactive, because all metabolism involves chemical reactions, and you can't live without metabolism. How many cells do we have in our body that are metabolizing right now? That's a question that you can answer, because I've already told you. Each lecture, I told you.
I know.
Not that I would want you to feel guilty.
I know.
Okay, baby. I mean, Denise. Go ahead.
I might be wrong. 37 million?
37, the number 37 is correct.
Billion?
Yep.
Billion.
37.2 trillion cells.
Trillion.
Trillion in each human body on average. Molly wouldn't have quite as many because she's not quite as big. Women and children have numbers in the high 20s or low 30s. Don't feel bad. Your mom's got a full complement. You will too.
How many would I have then?
Sorry?
How many would I have then? If I don't have any?
Probably around 20 trillion, 25 trillion, somewhere around there. But my point, Molly, is that in every one of those cells, in every second, there's all these chemical reactions going on that keep us alive. So we've got 37.2 trillion cells with about 1 billion reactions going on every second. So that's 37.2 trillion times 1 billion. That's the number of reactions that are going on in your and my body. Well, maybe a few fewer in yours, but you'll pass me, trust me. Anyway, that's what's going on right now, and that's all revolving around carbon, because carbon can make those connections and break those connections at just the right rate, right? So stable, you gotta be stable, but you also gotta be flexible. You can't survive on Earth if you're not, because everybody's got DNA, and your DNA is a certain way, and there's the environment, and your DNA, that's you, and the environment have got to get matched up. That's what evolution is all about. So if you and the environment are matched up, then you're adapted and you're doing great. But if they're not, you're maladapted, and I'm sorry, but you have to go extinct. That's just the way it is. Really sorry to tell you that, ma'am, but so that's how it works, and it works around carbon. Carbon is the central atom. You might think, well, come on, what about oxygen? Because after all, I mean, we live in an oxygenic world, right? We've only lived in an oxygenic world for 500 million years. Before that, there was no oxygen floating around in the atmosphere. None. It was a foreign atmosphere. If you'd been on this Earth 4 billion years ago, you couldn't have breathed the atmosphere for 1 sec. They're not sure what it was. They think it was mostly CO2, some nitrogen, bit of hydrochloric acid, bit of hydrogen. Horrible place. right? It's not fit for man or beast, literally. None of the things that are on the face of the earth right now could survive, except for a very few that are living in weird places, like at the bottom of the ocean, around hydrothermal vents, in hot springs at Yellowstone, in caves under the ocean, or they found life over 12 kilometers below the surface of the ocean. Now, there's a whole submarine world, subterranean world now, that's just starting to be discovered. Speaking of something else, it's so much to tell you. That's the point. And it's so hard to keep track of it all. That's why I rely on Denise.
Do you want to show Alvin? Not right
Well,
now?
at some point I do, yeah.
Okay.
Let me just finish about carbon, because that ties
Yeah.
in with the carbon cycle
Sure.
and with tectonics.
Sure.
And then we'll do the other thing, okay?
Okay.
So, basically, let's look at a cutaway of the Earth. Can we do
Okay,
that? I
yeah.
can't remember what number it is.
88 is the big one.
Okay. You remember this from last time, and just to reinforce this, okay? We're up here on the surface. Down here is a solid core. And this core is solid because there's too much pressure down there for it to be anything else other than solid. It would like to be a liquid, and this part's a liquid, but this part is too scrunched to be a liquid, so it's forced to be a solid. We're really lucky that that part there is liquid. Why? Anybody? Ferris Bueller's Day Off, gotta love it.
Anybody?
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 Anybody? If you were a class.
Okay.
Anyway, this part is liquid, and the reason that's a good thing is because it sloshes around. As the Earth turns, this liquid kind of sloshes around, and that sloshing makes it a dynamo. And the dynamo means electricity, electromagnetism, thanks to James Clerk Maxwell and his 4 equations, which came out in 1865.
I think I know where they are. Hang on.
It's okay.
No, I got the
That's
wrong
Newton,
one.
but-
I got the wrong one. I was close though.
Newton's cool. Newton's totally cool.
There, I got it.
I just discovered something, I want to emphasize that. I'm a learner. Like, I'm with you guys, I'm a student, I'm learning stuff every day. So I just can't wait to get here and tell you about everything I learned. I was just reading about structural coloration. Everything has a color. That color is a result of what wavelengths are being given off. Everything has its own unique signature of wavelengths. And I also knew that color was created in 2 ways. One way is by pigment. Plants invented a pigment called chlorophyll by which they can convert photons into chemical energy. There's all sorts of chemicals out there that are pigments, and so they make most of the color. But some color is created through reflection and refraction. So if you look at a peacock's tail, that peacock's tail is actually brown.
Wow.
But it looks blue and violet and all these gorgeous colors because the light is coming in. The peacock's feathers are arranged in such a way that they've got these little flat things called lenses. And they're arranged in such a way that light comes in and it either reflects, bounces back off, or it refracts, goes through and bends. And when it does those 2 things, the angles that it makes between the light going this way and that way create the colors that you see coming off the peacock feathers. So it's just a dull brown feather. But thanks to the way the molecular arrangement of those sheets, the light is reflected and refracted in such a way as that we see all those gorgeous peacock feather colors. Terry knows it better than most because he spends his time harassing those poor trout. And peacock feathers are big in fly tying. I used to have them all over the place, so I was big into peacock feathers. But oh, sorry, Terry, I didn't realize you were there. I wouldn't have embarrassed you like that. So yeah, I know peacock. And guess who it was that figured out how that works? It was Isaac Newton, and that's what reminded me of it.
Newton.
No, and him.
Okay.
Not him, no, Thomas Young.
Yeah. Okay.
So it was Newton and Young. Young was the guy who figured out light was a wave. He came up with this double slit experiment, which is just plain weird. So there he is, the last man who knew everything. That was his title. 1801. He proved that light was a wave, and he also, building on the work of Isaac Newton, proved what I just told you, that structural coloration is caused by the mechanism I just described. See how everything fits? I just learned that last night. over a few brownies. Anyway, where are we? Okay, now, oh yeah, now I get to tell you about ringwoodite. This is, oh, I don't know, this is cool. But first, let's go back to our cutaway of the
Yeah.
earth, just to make sure everybody understands. This is super important. So you've got the sloshy area down here, the outer core, and that's what's giving us the electromagnetic field. Why do we care about that? Because the sun is trying to fry us. The sun has UV, you've probably heard of it. It's that purple area in the electromagnetic spectrum I just showed you. That UV can be really hard on you. It's very harmful. So that sloshing of the core creates the magnetic field. We actually have a picture.
Can
of
I
it.
show that?
Yeah, sure, show them a magnetic field. Let's live dangerously. Oh, there it is. So out at the bottom and at the top, there's your magnetic field. And that is protecting us because the sun, let's say the sun out there, So the sun is, let's see, 149.86 kilometers away. It's firing all these, all this solar, it's called a solar wind. The solar wind is hitting us and it's spreading out around what is called the magnetosphere here, and that's kind of tailing out in that direction. So it's coming from the sun, hitting this, and then kind of tailing out. And that is protecting us from the sun and allowing life to live. Otherwise, it would be destroying our DNA every second and we would not be able to live or reproduce. And reproduction is one of the key elements of life. So, going back to our cutaway again, funny how you just, showing that picture of Newton just reminded me, right? Anyway, here's another cool thing. I might have told you this, but maybe I didn't. It's 6,371 kilometers from Merritt to the center of the earth, okay? And if you subtract 2,900 from it, which is the size of the core, so you go down 2,900, you hit the core. You go down 6731, I think it is, and you hit this. If you take that away from that, you end up with 3, 4, 7, I think it's either 2 or 3. And the reason I mention that is because that is exactly the size of the moon. We have within the earth, I noticed that one day. I started doing the math. I thought, can this be right? So I looked it up, and sure enough, it is. There's only 3 or 4 kilometers difference between the size of the moon and the size of the center of the earth. So just imagine we got this little moon down there underneath our feet all the time. It's so cool. And there's a lot of the reason there's so much iron down there is because we got it from Theia when Theia hit us 4.51 billion years ago. Isn't that cool? So now back to our, oh yeah, and the idea being, looking at our cutaway again, if we could have. The idea again being that, again, plate tectonics, there's your ocean, there's the underneath, there's your ocean, there's your land. The bottom of the ocean is this thin strip of crust. And the bottom of the ocean, the crust, is made out of metal that is called mafic, which means it's got a lot of magnesium and iron in it. Now the general term we use for metals that are dark, dense, and metallic, and have a lot of magnesium and an iron, is we call them mafic rocks, and the best known mafic rock is basalt. I'm sure everyone has heard of basalt. So what happens is the bottom of the ocean is made of basalt. Let us look at that one where we can actually see the subduction occurring.
Absolutely, yeah.
So the bottom of the ocean is a thin, dark, dense crust, and the crust over the land is lighter and floats. This is mostly granite, which is a felsic rock. I introduced these terms to you last week, and I'm going over them again. Mafic means metal, and it stands specifically for magnesium and iron. And the reason it stands for iron is that the Latin word for iron is ferrum. By the way, Latin was what the Romans spoke. Those guys,
Yeah.
they built those great roads and they had this empire. So the Romans spoke Latin, and the Latin word for iron is ferrum. So whenever we refer to iron, we call it either ferrous or ferric, and that will apply directly to the first life on Earth. We're going to have to deal with the words ferrous and ferric, because the first life on Earth, we think, if that life up in Nuvunatuck, if that turns out to actually be the earliest life on Earth, then that earliest life on Earth made its living, stayed alive by being able to convert ferrous iron, which is dissolved iron, into ferric iron, which is undissolved iron. That life form would have taken the electrons. I've harped a lot about electrons, right? Okay, so that primitive life form that existed 4.28 billion years ago, when the Earth had only been around for 300 million years, that primitive life form, if in fact that's what it was, stayed alive by converting dissolved iron, ferrous iron, into ferric iron by removing an electron. That changes the iron into a different kind of iron. And the difference is, if you've got a glass full of water with ferrous iron in it, the water will be clear. But if it's got ferric iron in it, it'll have this goopy, orangey, browny, pinky kind of sludge. And that is what's left behind by these bacteria when they convert iron from one form into another. So they convert it into another form, it comes out of solution, and whammo, you've got goop all over your plumbing appliances or your kitchen or whatever. I was carefully cultivating a little bit of goop in the kitchen, right where the spout comes up. There's a backsplash back there. Where the counter meets the backsplash, I noticed there was this little bit of pinky material, right? I thought, oh, this is great. That means there's iron bacteria in there, and they're converting the ferrous to ferric iron. And this pink goop we see is what's left behind. Then Denise came along and destroyed it. I hate it when people come along with these household. Anyway, but we don't know for sure. And I am jumping a little ahead of myself, but yeah, there's this place up in East Shore, Quebec, and right now there's a lot of activity up there because the word got out that the oldest rocks on the Earth were up there. And then the word got out in 2017 that they think wedged in the cracks between those rocks, they found this early life form. And then they revisited, some guys from McGill. In 2019, they wrote another paper on it because they had received a lot of criticism. People were saying, well, you know, that could have been formed abiotically, that is not by life. So these guys went back and they did a more thorough thing and they found some more fossils and they wrote up another paper and they're doubling down. They're insisting this is the oldest life on Earth. So right at the moment it's up in the air, but the oldest life on the Earth could be up in the Canadian Arctic. And even if that is not the oldest rock, there's another rock up in the Canadian Arctic over to the west and up further north called the Acasta gneiss. Gneiss is a type of rock, Gneiss. And the Acasta gneiss has been dated at 4.01 billion years old. So either way, Canada, baby, oldest rocks in the world. Before that, you would have had to go to Australia or Greenland, but we've taken over from Greenland and Australia. All right, looking at that cutaway.
Cut it back
again.
to the cutaway.
And then at the one,
Oh, yeah.
I want to imagine people, we're going to go down the I-5, and we're going to imagine what plate tectonics have done to the scenery as we're on our way down, right?
Absolutely.
There it is. Yeah, okay, okay. So let us imagine that we've gone down to San Francisco and we're heading back and we're coming up the I-5. Most people have been on the I-5, right? So you're driving along on the I-5. Over on your left is the ocean, except you can't see it because there's a row of hills between you and the ocean. And over to your right, when you get to a certain area, you get up high, and then you see these beautiful, great big huge volcanoes like Mount Shasta and that, right? All these gorgeous volcanoes, some of which are not by any means extinct. Matter of fact, some of them were only made 4 or 5 million years ago, so they're not all that old, so it's pretty recent. Anyway, you're driving back, you're driving up this big central valley, there's an ocean over there, there's a row of hills between you and the ocean, you're in a valley, and there's these big beautiful mountains, snow raising their lofty snow-capped peaks to the gorgeous blue sky, which 4 billion years ago was not blue. It was this horrible sort of orangey pink color because it was all carbon dioxide and methane and stuff like that. We would have gone, fallen over dead immediately. Well, we would have done it before that because there was 27 atmospheres worth of pressure, and at one point it was 280 degrees Celsius, so that's pretty warm. It would have been a hard place to be back then. But life started, this is the thing. Anyway, this is subduction. The oceanic crust, which is thin and old and cold, meets the the continental crust? Well, three things can happen. Well, no, two things can happen, basically. One is, one can go that way, and the other can go that way. And if that happens, you've got the San Andreas Fault situation, where you've got two continental plates locked, and they're each trying to go the opposite direction. And they build up pressure, they build it up and build it up. Finally, it gives, and you get an earthquake like the one in 1906 in San Francisco. They've had other ones since then. So here we are on our I-5, and we're coming back, and this on our left is where the ocean, the oceanic plate has subducted under the North American plate. And as it subducts, as it goes down, it takes the rock with it. And as the rock goes down, it gets hotter and hotter, but it doesn't melt because there's too much pressure. But then what happens is it takes water down with it. And the water hits a certain depth, and that depth is often around 660 kilometers down, at which point the water melts. Or the water the water acts as a flux, like when you're soldering, and it causes the magma, the rock down here to melt, and the melted rock then, because it's hot, so the melted rock is now trying to find its way up, just like all things do when they get hot, they want to rise, right? So the magma starts to rise up through the mantle, and then eventually makes its way through the crust up here and comes out as a volcano. So what's happening is two important things. Number one, all the rock in the world is being recycled. That's why there's almost no really old rock, because it's been being recycled while they're still arguing about when the recycling started. But I'm going to assume, actually, I'm going to go with what I think the majority opinion is tending towards, and it looks like it's tending toward the idea that plate tectonics started early. So we're going to assume that plate tectonics started by 4 billion years ago. And what it did was it started taking the rock and the carbon, remember, in the rock, down with it. When the rock gets to a certain depth, the water causes the rock to melt. The melt rises as magma, and if it can find a way through, it'll come out as volcanoes, and that's what created those beautiful big mountains that you see over to your right if you're coming back, or over to your left as you're going down. And all the mountains, Mount Meager, Mount Baker, Mount Shasta, Mount Rainier, all those lovely volcanic peaks were all created by magmatic activity over the last, I think it started 13 million years ago, and had different, I mean, I don't know a lot about that particular period because I've been concentrating on earlier periods in the Earth's history, but that's a bit the basic idea, which I've got right. And so that's how those mountains are formed. And what you've got is you've got the ocean, it's always the oceanic plates, and this subduction is recycling all the rock, and it's also recycling the carbon, and that's the important part. Plate tectonics, this is the message I'm trying to get across. Now I'm going to give you a break. Plate tectonics are the means by which the planet controls its temperature over long periods of time. That's how it does it. It takes carbon, like what happens is you've got the air. Let's say it rains. Okay, raindrop comes down and it goes through the atmosphere and it meets carbon dioxide in the atmosphere. The carbon dioxide gets in the water and forms a very mild carbonic acid. So each raindrop is like a little tiny carbonic acid bath, right? It's just very slight, very slightly acidic. You wouldn't notice it if you drank it. It's very slightly acidic. Gets down, hits the ground, soaks into the ground, reacts with calcium carbonate, which is limestone. Limestone is made by little sea creatures that take calcium out of the water, incorporate it in their shells. And so that's what clams and oysters and things like that do. Okay, so the carbon comes down, gets into the ground, gets into the rivers, and gets washed down into the ocean. When it gets to the ocean, all these little sea creatures grab it and start making houses out of it. But eventually they die, and so their little bodies sink into the bottom of the ocean. And over hundreds and thousands and millions, a couple of million years, they get all compacted down there, and then they end up getting subducted down into the ground. And what comes up out of the volcanoes is carbon dioxide. There's a number of other gases come out too. If you get a lot of sulfur dioxide coming out, it can actually cool things down for a bit. But mostly what has happened, nearly all volcanic eruptions, and all volcanic eruptions eventually, spew out carbon dioxide. So carbon dioxide is in the atmosphere, gets washed out by the rain, into the ground, down the oceans, down the rivers, to the ocean, to the bottom of the ocean, then subducted from the bottom of the ocean down, comes back up as magma, and comes out as carbon dioxide and forms new rock. So the youngest rock in the world is on the bottom of the oceans, and the oldest rock is on the land, because the oldest rock on land is felsic, which is light rock made out of silicon and feldspar, and the other kind on the bottom of the ocean is mafic, and it's made out of magnesium and iron. Magnesium and iron are heavy, silicon and feldspar are light, and so these light colored rocks, there's the Acasta gneiss that I was telling you about. So that's a rock that probably started out igneous, then it became sedimentary. The igneous rock broke down into little bits. That became sedimentary, sand, mud, silt. That got compressed down into the earth. When you mash something down, it gets hot, and so it gets hot and it metamorphizes. It metamorphizes and becomes, so it turns from its original thing into something else. And this has ended up as gneiss. So it started out as some kind of igneous rock, then it becomes sedimentary, then the sedimentary gets recycled, subjected to heat, and it gets altered, and it finally ends up, it goes into schist, and then it gets altered into gneiss. This is a piece of gneiss, except it started out as a more mafic rock with more metal, and that's why it's darker. Okay, let's continue on after a quick break, okay? Thanks very much.